Hello, Professor Mitchell. Thank you so much for being with us today at ML Done.
My pleasure.
So I'm just going to go over a few of the interesting questions and really look forward to having a nice interview. And so first foremost, let's just, could you just introduce yourself briefly?
Sure. My name is Tom Mitchell. I'm a professor at Carnegie Mellon University. I've worked in artificial intelligence for many years, and especially in machine learning. I started the world's first machine learning department at Carnegie Mellon, and really like this field. I'm very optimistic about the future of AI.
Perfect. That's great. So could you just tell us a little bit about how you became interested in machine learning in the first place? How did it all start?
Yeah, actually, the truth is, I've always been interested in learning, and including how people learn, and intelligence, and how people are intelligent. And in school and college, I had a lot of different majors because I couldn't find the right one for me. And one I considered was psychology, because I thought it'd be very interesting to study intelligence and people. But in the end, I felt that there just wasn't enough observability of what's going on in people's brains. When I was in college, it was before the advent of brain imaging machines, which happened around 1995. And so in the end, I decided we really can't study human intelligence very well because we can't look inside. And so I decided to go for studying intelligence in computers instead. And so that's kind of how I got interested in this. I will say that when brain imaging did become available in 1995 or so, fMRI, for example, it only took me a couple of years to hook up with a psychology professor at CMU who was doing brain imaging and to try to start looking at both intelligence in computers and at least brain activity during intelligent processes in humans.
Wow, that's amazing. So also, could you just tell us a little bit about your current area of research?
Let me tell you, there are a couple areas. But let me just pick out one that I'm enthusiastic about. I'll call it conversational machine learning. When I look at the field of machine learning, and actually when I want to predict the future of machine learning, what I think all you need to do if you want to predict the future of machine learning is take a look at how humans learn and computers don't yet. And so humans learn statistically by gathering different experiences and generalizing from those. And computers are very good, quite good at that. But people also learn a lot from conversations and from instruction, in fact. If you were to hire me, for example, as an assistant to help you, manage your program and schedule meetings and do some of the post-processing, you might hire me, but you would certainly, if you did, then instruct me how I should do things. You wouldn't expect me to learn those things by watching you do it 10,000 times and then generalizing from those examples. That'd be crazy. You'd fire me if that was the only way I could learn. So, it's kind of obvious that people, even though we do learn statistically, we also learn a lot from instruction. And so I think one of the potential paradigm shifts in machine learning in the coming years is to build systems, machines, that learn both statistically and from conversation. One reason I think this is the decade when that shift might happen is that it's only the last 5 years that we've even had conversational computer systems that work at all. You know, you can have very simple conversations with your phone, like, hey, what's the weather? And then it tells you. You can't have conversations like this. But I think it's not out of sight, and this is one of our ongoing research efforts, to build, for example, a phone where you could teach it, instruct it to do new things that it can't do now.
Instead of waiting for them to develop a software or an app to do whatever it is that we want, basically, right?
Right. And I think a lot of the things that people would use phones for will never be developed as apps, just because there's not a mass market for them. There is a mass market for a weather app because everybody's going to use it. But for example, I want to be able to say to my phone, whenever it snows at night in Pittsburgh, wake me up 30 minutes early because I want to get to work on time. And if I say that to my phone now, it simply says, I don't understand what you're talking about.
Yeah.
But in the future, I think I should be able to instruct it by saying, oh, well, if you want to know whether it's snowing, you open up this weather app, and right here where it says current conditions, if that says SNOW, it's snowing.
Yeah.
If you want to wake me up 30 minutes early, you open up this alarm app and you subtract 30 from the number here. So if I could instruct it the way you would instruct me, then it's a completely different ballgame than statistical learning.
Absolutely, absolutely. That's very interesting. So I was actually going to ask you about conversational learning, but so we sort of covered that, I guess. So I'm a big fan of your book, the book entitled Machine Learning, that I think you published, I think in 1986. Actually, when I first started my PhD in University College Dublin in Ireland, a friend of mine, Ellen Rush, she actually told me, look, you're going to love this book. On page 97, you're going to fall in love with the backpropagation algorithm, the way he has taught the whole thing. She also asked me to tell you this. She's a big fan like myself. But so what I'm interested to know is that, how does it feel to see that this book is still popular? And would you say we have come a long way since 1986 and the materials covered in the book?
Yeah, so I did publish a book in '86 along with Jaime Carbonell and Richard Mikulski called Machine Learning. That's not the textbook. That's a collection of research papers. The textbook you're mentioning actually came in 1997, but still long ago. And it also has the name Machine Learning, so my apologies for causing the confusion by equal titles for two books. But, you know, I still, what can I say about the book and what has happened? A lot has happened, of course, in machine learning in the last 25 years. It's almost 25 years since that book came out. But the fundamental principles that define machine learning, like overfitting is going to happen if you're not careful, and there are statistical theoretical bounds on how much training data you're going to have to provide in order to assure that your learner outputs a hypothesis with some bounded error. Those kind of fundamentals haven't changed, of course. And so when I look back at that book, I think it does actually, many of the fundamentals that I teach now, most of the fundamentals that I teach now, were already there in 1997. What wasn't there, of course, was things like kernel machines, support vector machines. They came after 1997. So there are newer algorithms that have come out. The biggest thing that has come out, of course, is deep networks and the huge burst of energy and new algorithms and new approaches that have come out of deep networks. So, so to me, I think when I teach my machine learning course now, I find that about half of the material that I cover is covered in the textbook, but there's another half that's happened. And it's fun to teach the course. It gives me a chance to actually write up some notes and some draft chapters on the newer material.
Perfect. That was really interesting. And yeah, so I know that at Carnegie Mellon University, you and your team have developed these two continuous learning agents, if that's the right word, NELL and NEIL. If you could just tell us a little bit about both of them, and also tell us how long have they been learning what exactly?
Yeah.
Thanks.
So I'm glad you asked this question, because one of the research areas in machine learning where I think we don't have enough effort is what I would call never-ending learning. Most of the work in machine learning assumes you have a data set. You're going to run your algorithm on that data set. You're going to output a learned hypothesis. You're going to output an answer. And then you're going to maybe use that to classify future medical patients or whatever. But there's very little, but that kind of, what should we call it, single event learning is very different from, again, what humans do. You and I learn continuously for days and weeks and years and decades. And we learn not one thing, like let's diagnose a medical patient. We learn very diverse sets of things, how to crawl, then how to walk, then how to run, then how to ride a bicycle. And we learn them in a curriculum that runs from easier things to increasingly complex things. We get synergy among seemingly very different things. Maybe we're learning calculus in school and we're learning physics, but it turns out calculus is the key to understanding a lot of concepts in physics. And so when I look at people learning over years and notice those characteristics, diversity of things they learn, easy to harder things, getting synergy among different perspectives for looking at the same thing. I think we need more work on how to, in machine learning, take advantage of those same kinds of things and get those same kind of capabilities. So that was the motivation. So NELL, for example, stands for our never-ending language learner. And NEIL, which by the way was primarily developed by my colleague Abhinav Gupta, stands for an ever-ending image learner. But both of them are systems that look at the web and try to extract more structured information, learning from the unlabeled web, if you will. So for example, in NELL, NELL's job really is to build up a structured knowledge base that contains the information that's there in unstructured text on the web. And so, for example, NELL has over 100 million beliefs, belief triples, you might call them. It believes, for example, that Bill Gates founded Microsoft. It believes that carrots are a vegetable. It believes that love is an emotion. It believes that roses represent the emotion love. And it believes that t-shirts should be worn with jeans. So very diverse kind of belief triples. The thing is that it learns those with very little human supervision, a little bit, but mostly just from running continuously and looking at redundant information on the web. For example, if you look for evidence that Bill Gates founded Microsoft, you will find at least tens of thousands of independent text statements that say things like Bill Gates founded Microsoft, but some will say Gates founder, Microsoft founder Bill Gates spoke yesterday, blah, blah. So they'll use different phrasings, but they're different phrasings of the same belief. And that kind of redundancy on the web really fuels the kind of ongoing learning from unlabeled data that NELL can do. Now, I have to tell you, we started NELL in January of 2010. We started it running, and we learned a lot from that project. But at the end of 2018, I decided to pull the plug on NELL because I think we had learned from that experiment what we were going to. We wrote up a paper in the CACM, Communications of the ACM, summarizing the lessons from NELL. But at that point, I decided that if I want to make the most progress in understanding never-ending learning, I should stop that software system and design a new architecture that has some properties that I believe will make a better never-ending learning solution. So for example, NELL had there were some really good ideas in NELL about how to use unlabeled data that happens to say the same thing with different phrasings, the Bill Gates example I gave. But one thing NELL could not do, for example, it could not self-reflect. It could not look at what it was doing and decide, oh, I've learned about all the countries that exist. The rate at which I'm finding new countries, there seem to be between 100 and 200, and it's not changing anymore. As a human, I can look at NELL and I can make that statement, I can observe that. But the architecture of the software was not able to self-reflect on how am I doing, and therefore, where should I put my learning effort next? NELL continued to search for new countries, even though I hadn't found any in 5 years. And it also continued to search for, new beliefs about new things that were happening, which it should be searching for. But it couldn't tell the difference because it didn't have a self-reflection capability. And I believe, having run the NELL experiment, that we need architectures that are much more self-reflective so that computer systems can observe what are they good at, what are they poor at, and therefore what kind of learning tasks should they focus their resources on. So we're in the process now, I'm in the process now of trying to design a new architecture and look at never-ending learning in some new ways.
Have you ever, I wonder, entertained the idea of some sort of a adaptable architecture that can just change depending on what the concept or what the context is?
Yeah, that's a great idea, I think. And really the question is, if you build an architecture, say some agent that has some sensors into its world, if the world is the web, those sensors are cyber sensors, but that's fine, and some effectors to change the world that it's working in. I think one of the key questions to be answered in designing that architecture is what parts should be frozen and not learnable, not changeable, versus what are the parts that should be plastic, that should be accessible, open to learning and to change. And I think I'm glad you asked that because I've been thinking about that question a lot. And I believe you do need some frozen parts, some parts that are not going to change in order to set up enough basic structure to allow learning to work successfully. And I love your question. I consider it one of the key open questions about never-ending learning.
Yeah, perfect. Thank you so much. That was very interesting. I can't even, it's sort of unfathomable to me to have this gigantic model that has been learning for what, 8 years, 2010, yeah. 2000, it's amazing. So let me just jump back to, this one is something that I started wondering this when I started learning about neural networks, that there are obviously differences between an actual neural network compared to an artificial neural network. I wonder if you could tell us about the key differences between the two, and would you say that it is worthwhile our research in machine learning to actually focus more on, you know, making that gap vanish, so that maybe a system that is more similar to an actual neural network might give us capabilities that otherwise we wouldn't have.
Yeah, I think that's a very interesting and kind of deep question, right? The originators of artificial neural nets were largely inspired by biological neural nets. And there are plenty of researchers out there in cognitive neuroscience who use computer artificial neural nets, let's call them, to try to build models of human cognition. One of the biggest, let me put it a different way. One way in which those cognitive scientists try to match up what you see in the brain with neural nets is, well, I'll give you a particular project that's done by Sharmistha, my PhD student, co-advised with Partha Talukdar. And in that research, we've been collecting brain image data while people read sentences. Simple sentences like the dog found the bone, or the bone was found by the dog. Sometimes it gives the same meaning, but phrased in different ways like that. And we record the brain activity word by word as people are reading those sentences one word at a time. We record the brain activity to millisecond time resolution. By the way, it takes 400 milliseconds for your brain to understand a word. So we have very fine detail in terms of the timing. Recently, we've been interested in the question, can we use the state-of-the-art natural language models like BERT to model what's going on in the brain? So Sharmistha, also I'd say Maria Taneva is another student working on this, and my faculty colleague Layla Webby also. And then Sharmistha Jat, by the way. So anyway, we're all looking kind of at this question. And so what we've done is we've collected data on particular sentences that we've shown to people, and we have their brain activity. We give the same sentences to BERT. And now we watch BERT's hidden layers incrementally changing as we give it word by word the next word in the sentence. And now we have BERT's representation in an artificial neural network of the meaning of the sentence, or at least the part of the sentence that it's heard so far. And what we do is we set up the machine learning problem of predicting from BERT's representation of the sentence meaning, predict the neural activity in the person's brain at the same stage in reading the same sentence. And what we found is, yes, this works to a surprising degree. It is possible to then, for example, give a new sentence that hasn't been seen during training to both the person and to BERT, and use that learned mapping, for example, to predict the brain activity well enough that you can distinguish whether the person was reading sentence 1 or sentence 2 based on the prediction from what BERT does for the sentence. Okay, so we're trying to set up this research paradigm that really pushes the limits on to what degree can we use these artificial neural networks as models of brain activity. And I'm excited about that research direction. But you asked also, what are the differences? And one of the big differences in neural activity in the brain versus the representations in artificial neural networks is that the artificial neural network activities are numbers, that, real valued numbers that get computed. But in the brain, they're spiking neurons. And neurons spike at different rates, and sometimes two neurons will spike synchronously. In artificial neural networks, there's no notion of synchrony and there's no real notion of spiking. And to the degree that those turn out to be fundamental in understanding brains and how people work, then that mismatch is going to hurt us. So just one quick piece of evidence on that to consider. It's not clear to me, or to anybody as far as I can tell, how the brain binds arguments. For example, if I say, Mary hit John, or John hit Mary, based on brain activity that we can see, we can't distinguish those two sentences except from the sequence of the words. But we can't see where the binding of the argument that John was the hitter and Mary was the hittee, or the other way around. We don't know where that binding is. And one hypothesis is that binding is done by the synchronization of this kind of spiking. If that turns out to be true, then we're going to have an awfully hard time modeling with BERT and other artificial neural networks that kind of binding phenomenon. Just so there's just an example.
That was amazing. Wow. It's mind-boggling. So you had so we talked about conversational learning, and yeah. So just sort of a non-technical question. So in your opinion, the current machine learning venues, especially I guess the big names in machine learning conferences, for example, would you say that the review process is as fair as it should be? And if it's not, how would you say it could be practically improved?
Oh, that's a great question. It's not as fair as it should be. And that statement holds for every field of science and every publication. I mean, there are always papers that, in retrospect, should have been gotten out to the public faster and they were rejected. You can always find those cases. So I think of reviews as a probabilistic kind of decision process. And it makes some mistakes, especially at the border. You know, if you rank papers from, let's say, 10 years later, actual importance from most to least important, there's some spectrum. And I think, you know, you'd like to publish all the papers that you have space for that are above some threshold of importance, let's say, in quality. I think, you know, conferences and journals, because of pragmatics of finding people and getting them their attention to review and finding the right people who have the right background, instead of having a nice sharp ability to say where on that threshold should they accept versus reject. It's very fuzzy, especially around that threshold. So there are plenty of papers on the wrong side that get accepted and on the right side that don't, especially if they're close to that threshold. Now, humans are imperfect. What are you going to do? So, but I think that's just what it's like. And when I've had papers that were, let's say, rejected when I thought they should have accepted, I just consoled myself in saying, well, if it was close to the middle anyway, probably I don't want to publish it. Here's the other thing I tell my students, which I believe deeply. There are a lot more papers written than there are widely read. So the number of papers that are widely read, the percentage of papers that are widely read is really small, probably under 10% of those written. So if you want to have your next paper, if you want to have your paper read, I'm sorry, not written. If you want to have your paper read, what you need is that your previous paper was one of those widely read. So you should only publish papers that are going to be in, like, let's say, the top 20% anyway, because if they're close to the bottom of what was getting accepted, they'll get accepted, but maybe not widely read. And that won't help you the next time somebody sees your follow-on paper. So anyway, I just kind of take it all with a grain of salt. I don't have a magic solution.
Yeah, that's true. So you don't think that there's a systematic issue there? It's just the human nature?
I think it's human nature. I think there's also a systematic bias toward people who are well known that's unfair. I don't know how to get around that, but I think that exists as a bias. Also, probably even toward institutions that are well known.
Okay, got it. And just the last question. And I've observed this particular issue a lot. So we have so many libraries that are already out there that people can just use, and with just a couple of lines of code, they can just build this gigantic neural network that can do fancy stuff. But if you sit down and talk to some of these people, you realize that they haven't really understood the nitty-gritty details behind the scene, like what's really happening, even very superficial understanding about the math, if ever anything, really. And this is happening a lot. I wonder if you think that's okay. And if not, I mean, what should we do about this?
Yeah, I think you bring up an important phenomenon, and I've noticed it too. So it's just about everybody. It's now so easy to assemble a program whose components you don't really fully understand. Using systems like Tensorflow and Pytorch. My attitude toward that is I am thrilled that TensorFlow and Pytorch exist and the other packages that are out there. I'm thrilled that they exist because it does enable you to build complex systems with much less effort. But they bring with them a kind of unintended consequence that you can build these systems that you really don't understand yourself. And so I think it's part of the new software engineering of machine learning systems that you have to, if you're going to be successful, in the end, you're going to have to understand what those components really are doing. And so, for example, in the machine learning class that I'm teaching this semester, I'm having my students program systems not using those packages, but from the ground up, so that they understand how to, what is every detail of the code, because it's their code, they're building it. I'm going to encourage them at the same time that in the future, they, not for homework in my class, but when they're trying to build systems, that they actually do take advantage of these packages that are out there. But I hope by the time they come out of the course, they'll know more about the fundamentals and, what does it mean to drop out? What does it mean to,
absolutely,
these things, you can turn them on and off as switches, but if you don't really understand what they're doing, or you really don't understand the mathematical form of the function you're learning, you can make a lot of avoidable mistakes, and you can avoid them if you really understand the details. So to boil it down to a sentence, I think it's great that those packages exist, but we need to, as a community, find ways to be more aware of what's going on in the package, in the systems we build on top of those packages.
Absolutely. Well, that was perfect. I hope that you enjoyed the talk as well. I enjoyed it a lot, actually.
Yeah, thank you very much. This was fun, and good luck with this whole sequence you're doing.
Thank you so much. It was indeed a pleasure to have you, and I hope that you have a lovely evening.
Okay.
Thank you so much.
Bye for now.
Thank you. Bye.